So, welcome. Welcome to the 30th Hintze lecture in the Department of Physics at Oxford. And we've something different for you this evening, which I'm sure you'll enjoy. I think you've realized we got something different for you. That's why the place is packed. So I'm Stephen Smart. I'm the Philip Whetten Professor of Astrophysics, a position created by the university in 2002 due to the benefaction of Philip and Roswitha Whetten, who are both with us tonight. I'm the director of the Hintze Center for Astrophysical Surveys. And as part of that, we host this biannual lecture series, the Hintze Lectures in Astrophysics. This is the 15th year, the 30th Hintze Lecture. My predecessor, who held the Whetten Chair, Roger Davies, he instigated these lectures back in 2010. We've had fantastic communicators, including 2 Nobel Prize winners, and you're going to have more of the same tonight. So on this occasion of our 30th anniversary, it's a real pleasure to thank Lord Michael Hintze and Lady Dorothy Hintze for their ongoing generous support of astrophysics in Oxford through the Hintze Family Charitable Foundation. Without their support and real enthusiasm for these events, they wouldn't happen. They're the reason you're here tonight, and our guest speakers are here tonight. And it's a pleasure to welcome the Chancellor of the University of Oxford, Lord Haig, to his first Hintze lecture. Lord Haig has visited the Department of Physics, and we thank you for the support and hope you enjoy the event. The support of Lord Michael and Lady Dorothy is making a real difference both to the science we do here and to the lives of young people. The DPhil students and the fellows in the Hintze Center, your funding has made a real difference to their scientific careers. It enhances the whole of astrophysics at Oxford. And on this occasion, to mark the 30th anniversary lecture, we've made a video for you, and we want you to hear this directly from the people that your lives have changed. I'm hoping the sound plays.
I'm delighted to be able to speak to you on this occasion of the 30th Hintze Lecture. The series has been funded by the Hintze Family Charitable Foundation from its start. We owe a great debt of thanks to Dorothy and Michael Hintze. I unfortunately cannot be with you in person today. I am in Munich, chairing the Science Advisory Board of the Max Planck Institute for Extraterrestrial Physics. And in that role, I will be with Reinhard Genzel, who shared the Nobel Prize in 2020 with Roger Penrose, who you will hear from shortly. 15 years ago, I met Michael Hintze and had an energetic conversation with him where I discovered his fascination with astronomy and cosmology. And that led directly to the foundation of the Hintze Center for Astrophysical Surveys.
The Hintze Center is a group of scientists at the University of Oxford working on the theme of surveying the sky with the most powerful telescopes on Earth and in space. And what brings us together is trying to answer the big questions.
In the past years, I've been working a lot in preparing what is probably one of the largest astrophysical surveys of the next decade. This survey will be carried out with the Vera Rubin Observatory. My main research goal is to measure the expansion of the universe using this particular class of cosmic explosions called supernovae 1A.
I'm a theoretical astrophysicist, so what I do usually is I take in a lot of the data that the telescopes that the Hintze Center uses, and I try and apply mathematical models to explain this data. And so what that allows us to do is learn more about the things that we're seeing, trying to understand the underlying physics that's governing these astronomical sources.
I investigate galaxy formation and evolution, especially focusing on the most massive galaxies in our universe. Right now I'm carrying out very interesting and intriguing projects looking for relic galaxies. Those are the fossil record of the first galaxies that ever formed in the universe.
Hintze funding has allowed us to create this incredible virtual space where we can bring in some of the best young researchers from around the world to work on some of the most cutting-edge data sets in astrophysics.
The thing I'm most proud of is recruiting the best talent in the world to come to Oxford. and to give them an opportunity to flourish, to have an independent scientific career for 3 years, working with us on projects of interest.
I thoroughly enjoy connecting with people who are tackling so many different questions from different angles, different perspectives, and at different scales. The environment really pushes me to think bigger, and I enjoy the collaborative and creative aspect of it all.
Being a Hintze Fellow has allowed me the independence to undertake a more long-term project. And in particular, this model that I've been building has been the last year and a half of my research, which wouldn't be possible in a different type of academic position.
Being a Hintze Fellow has given me the freedom to pursue the research that really interests me. And that means that when interesting things crop up in the data or in other papers that I read, I've got the freedom to then pursue new lines of research that are really interesting.
You need the kind of fellowships that people will recognize. And to do that, you need to nurture those fellowships. You need to, it takes years to create a fellowship that people will name check with an approving nod. The Hintze Fellowship has that kind of recognition. I think it's one of the top fellowships in the world that people aspire to get.
It has been wonderful to see how the early fellows have now secured senior positions in eminent departments throughout the world, and often the graduate students have gone on to prized fellowships and are building their careers as a result of being here in the Hintze Centre.
So on to tonight's event. It's a pleasure to welcome our two speakers in a different format than our usual event. Janna Levin from Columbia University and Sir Roger Penrose. Janna Levin is the Clare Tow Professor of Physics and Astronomy at Barnard College of Columbia University. She's a Guggenheim Fellow, author of many books such as How the Universe Got Its Spots, Black Hole Blues, and The Black Hole Survival Guide. In her scientific career, she's worked on rotating black holes, merging black holes, the cosmic microwave background, and our cosmological model of the universe. So Roger Penrose, an icon of physics in Oxford, the UK, and around the world. I can't begin to describe Roger's influence in mathematics, theoretical physics, and cosmology, and I would be here too long if I tried. And you're here to listen to Roger and Janna, not me. So Roger, one of the greatest thinkers in physics in the 20th, 21st centuries. Many of you will have read his books, not just on physics, but on consciousness and quantum mechanics. Black holes are fascinating objects, currently not directly observable in electromagnetic radiation, but only visible through their strong gravitational influence on matter. That was recognized by the Nobel Prize in Physics in 2020, one half the discovery of the supermassive compact object at the center of our galaxy, and the other half awarded to Roger for the discovery of that black hole formation is a robust prediction of the general theory of relativity. So let's hear more about this from the two world's experts. Janna will start us off with some thoughts and words about black holes and their relevance in current thinking in cosmology and astronomy, and then have a conversation with Roger. So please join me in extending a warm welcome to both.
Thank you so much. I've been asked to do a brief tour of the universe in black holes before I joined Sir Roger in conversation, so thank you for indulging me. I wanted to begin with a very big picture view of the cosmos. This is not a cartoon or an animation, it is actually a digital atlas, meaning that it was built by observations of the universe where each object is placed as accurately as we understood it at the time. What you're seeing here is a tiny sampling of the satellites orbiting the Earth. If you were an alien civilization in a nearby star system, you might try to discover a techno-signature of our presence in the universe by looking for that, but as you can see, as you get outside our solar system, it just disappears entirely. We'd be very hard to spot, as noisy as we are. There goes our solar system, and what I want you to notice right now is that we're approaching the Milky Way galaxy, which looks like a riff on the sky because we're in the plane of the galaxy. So our galaxy is a collection of hundreds of billions of stars, and there it goes. It's gone. Right now we're panning out into billions of light years distant, and every object you're seeing is a galaxy or clusters of galaxies, the largest structures that we understand in the universe. And the dark patches are just the regions we're unable to observe at the moment. Right now you're seeing the light left over from the Big Bang. That's 14 billion years old, the very cool afterglow of the primordial explosion. And now we're zooming back in past all the galaxies, back to our Milky Way. And the aspect to take in of this scale is that there are as many galaxies in the observable universe as there are stars in the Milky Way. And there are probably more planets. In our own Milky Way galaxy, about 1% of those stars become black holes. So there's hundreds of billions of black holes. It's a lot of black holes. Now, the black hole began initially as just an idea. It was a thought experiment. The idea was imagine the mass of a star crushed to a point. There was no sense that this was plausible or possible or it would exist in reality. It was really a mathematical exercise. In 1916, Einstein publishes his general theory of relativity. It's World War I. Within 6 months, he gets a message from the astronomer Karl Schwarzschild, who had enlisted as a German infantry soldier, was on the Russian front, and he writes Einstein this unreasonably optimistic letter. He writes him and he says, "As you can see, the war has treated me kindly enough, despite the heavy gunfire, to allow me this walk in the land of your ideas." I mean, who says this when they're being allowed? They're in the trenches, between calculating ballistic trajectories. He's reading the proceedings of the Prussian Academy of Sciences, So Schwarzschild's notion was, imagine we crush all the mass of a star to a point. He uncovers the curved space-time in the context of Einstein's general theory of relativity. And the all-important observation in that solution, and it's taken many decades to pick apart, is the occurrence and the existence of the event horizon, the region beyond which not even light can escape. That is really the defining feature of the black hole. And of course, it did not have the name black hole for many decades. Schwarzschild sadly dies within 6 months, I believe, of writing that letter, of finding that solution from an infection contracted on the front. Now, Einstein was very impressed that this solution, which was very idealized, very mathematized, could be found so simply. He's very impressed with this, but he thinks black holes, which are not yet named, are anathema, that nature will simply defend us, protect us from their formation. And it's almost as though nature tries everything that can be tried. So nature thinks of a way to make these black holes by killing off very massive stars. It was actually Oppenheimer who is very interested in nuclear physics for agnostic reasons, both because he's interested in the cores of stars, but also because he's building a nuclear weapon, is thinking about stars and their life cycle. And he writes a paper which is one of the first arguments about matter collapsing. And he argues in his paper with his student Snyder that under unhindered gravitational collapse, a black hole will indeed form. Again, I'm using the name anachronistically. They had not yet been given that moniker. The paper is published in 1939. Sir Roger and I were just discussing this paper. It's published on the day that the Nazis advance on Poland. The paper falls into obscurity. If you watch the film, Oppenheimer, there's a vague reference to it you can catch, where they open the newspaper and they say, "Oppenheimer, no one's going to pay attention to your paper now." And nobody paid attention to his paper except to criticize it. People didn't believe he was right. But indeed, the universe abounds with black holes, we now understand. The name was coined, by the way, by the grandfather of American relativity, John Archibald Wheeler, who said, "The star fades from view like the Cheshire cat. One leaves behind only its grin, the other only its gravitational attraction." I have here a mathematical model of falling into a black hole. Should you not have paid attention in this lecture, and you come across one, you should not cross this event horizon. So what does the event horizon look like? It looks like just a shadow cast on the sky. The event horizon is simply the region beyond which light cannot escape, so it must be dark. It's the darkest, in some sense, conceivable phenomena in the universe. It surprises people to know you could fall across the event horizon of a black hole and be quite unharmed. Nothing spectacular should happen. It should be as undramatic as stepping into the shadow of a tree. And in fact, black holes can be bright on the inside. All of the light and the matter can fall in behind you in a big bright flash of light as you see eons unfold in the galaxy, but you're never making it out again. So it's kind of like a near-death experience, but it's a total death experience on the inside. It's a bright flash of light. So the interesting thing about black holes that people often forget with all this kind of monster talk about destructive black holes is that they are tiny for their heft. That is the entire point. If our sun, which is 1.5 million kilometers across, were to become a black hole, it would be 6 kilometers across. It would be tiny. A 10 solar mass black hole, our sun will not become a black hole, it's not heavy enough. A 10 solar mass black hole is city-sized. And how do you find this tiny dark shadow that emits and reflects no light in a galaxy sparkling with luminous stars? It's incredibly challenging. Quite ironically, this is a cartoon. This is my only cartoon. The black hole, which is the darkest phenomena conceivable in some sense, becomes the brightest. Black holes have tremendous power condensed in their heft, in their very small size. If you imagine dropping a penny from the Empire State Building, all my references are New York. So you drop a penny from the Empire State Building, you know it's coming down hard, a lot of energy by the time it reaches the ground, dangerously so. Here you're imagining cannibalizing a neighboring star, all of that matter splattering onto a tiny city-sized dense region of space-time, and the energies involved are tremendous, and people began to suspect that some of the bright signals and X-rays and gamma rays and even later radio waves, that what they were seeing were in fact black holes. Now, nature thought of more than one way to make a black hole. We find when we look in our own galaxy in the direction of the constellation Sagittarius that there is a black hole beyond that constellation, 26,000 light years distance, that is 4.5 million times the mass of the sun. This is not something that formed as the death state of stars. We don't know how these supermassive black holes formed. They can be millions or even billions, maybe tens of billions of times the mass of stars. We think they're formed very early in the universe's history and that they lurk in the centers of every galaxy. We are orbiting this here's Sagittarius star, have you not met yet? We are orbiting this supermassive black hole as surely as we are orbiting the sun. It is part of our history and it is part of our future. And it's reasonable to suspect that nature may even make microscopic black holes in the Big Bang. So there's something about black holes that is unlike any other astrophysical phenomena. They're fundamental in some way. They share characteristics, and Sir Roger proved much of this. They share characteristics that sound like those of fundamental particles. And there's something, maybe we can talk about that a little bit. But before I sit down with the legend, I have to show you this paper that Sir Roger drew by hand for his 1965 classic work, Gravitational Collapse and Space-Time and Singularity, Space-Time Singularity, Gravitational Collapse and Space-Time Singularities. I'm sure you've all read it. It is an absolutely stunning piece of work. This is a mathematical object, and it can be read by the initiated as a mathematical object. It's the pinnacle of the proof of this paper that takes up less than 3 journal pages. And in it is a condensed and concise proof that the end state of unhindered gravitational collapse is inevitably, and this is a huge moment in the history of theoretical physics, inevitably the formation of a black hole in the context of general relativity. It is not an idealized mathematical model. It is not a simplified, even what Oppenheimer did in 1939. It is a generic and inevitable consequence in general relativity of gravitational collapse that you create a black hole. Let me just read a couple of things for you in this drawing. This slice of space is 2 dimensions of space. We suppress 3 dimensions when we draw such things to fit them on the page. Time runs upwards. You can see he wrote time helpfully right there, the little arrow. Take note of the little eyeballs on your left. I appreciated the eyeballs. I always really appreciated that, Roger. So as the star is collapsing, he's showing you these what are called light cones. Imagine light fanning out in all possible directions. The light cones tell you at the cosmic speed limit of the speed limit of the speed of light where they can make it in space. And the eyeballs can see the star collapsing. They're catching these light cones, but eventually they begin to tilt inward. And at that point, no light is escaping. The event horizon forms, and inside it hides and obscures and protects the rest of the world from the singularity inside. Even in 1965, Roger suggested that the singularity was not possible. It was there, it was inevitable in his mathematics, it was inevitable in the general theory of relativity, but he felt that maybe quantum mechanics, and I want to speak for you because we're going to ask you, maybe quantum mechanics took over there, rewrote that story, maybe space-time was no longer describable by these classic means. And still, that is one of the great mysteries that we grapple with. I will say that this drawing and really the proof it represents is one of the great masterpieces of 20th century science. So thank you so much for indulging me, and please join me in welcoming my companion for tonight, Sir Roger Penrose. We were talking about you making these drawings.
Yes, well, I usually drew my own pictures.
You didn't trust anyone else, you told me.
Well, you see, I started off by getting the professionals to do it, but so often they would make a little mistake, like this line should be behind that line, not in front of it. And so I'd say, no, you've got to correct that. And then this one would be wrong. So I thought, I'll just do it myself.
Now, a lot of your mathematical inventions, often you would create a visual counterpart. You have, of course, Penrose tilings, which were very original, and you made actual mathematical discoveries with the Penrose tilings. And, of course, the Penrose diagrams, which map an infinite space-time into a finite region. Did you always think of yourself as a visual thinker? And did you always think of math visually?
I was always very much a geometrical visual thinker. I remember when I was at school thinking that when I went to university, if I did maths, I would find people who thought like myself. And instead, I found people who thought very differently from me. I found that probably there were about 3 people in a class of about 15 who thought visually. On the whole, people who did maths didn't think visually. They were more thought in terms of equations and things like that, which I could do.
Equations are nice.
They needed to do that sometimes.
Yeah.
Except I often converted them into little diagrams. That was what I did for my thesis. Except I had to change them back into little
In your thesis, they made you change them. Did you think, when you were writing this paper in 1965, that it would have the impact that it did? I mean, let me ask you a question this way first, and then I'll ask you that again. When you were working on this paper, still black holes had not been named.
Oh, yes. No, that was not true. Yes, they hadn't been.
And
well, perhaps I should clarify a bit here, you see. At the time when I was doing this work, that people had seen the effects of, quasars. They didn't know what on earth they were. And people had pointed out this paper that you mentioned.
The Oppenheimer paper.
Oppenheimer and Snyder paper. But the thing about that paper, there were 2 very, very special things. One is that the material that was collapsing was dust, which means it has no pressure. That's relatively unimportant. The main important thing about it is that it's exactly spherically symmetrical. So as it falls inwards, there's nothing to stop it because there's no pressure. it falls inwards towards the center, and since it's exactly symmetrical, then it has to hit this, become this singular point where everything crowds in at the center. But that's not realistic at all. And people would say, well, no, we can't take that picture seriously, because normally it would swirl around in a complicated way, swish around, and come squirting out again.
So no singularities, no black hole was the thought.
So that was, I think, the common picture. Also, it was the view, because there was a paper by two Russians, Lifshitz and Kalatnikov. And in this paper, they had demonstrated that in the general case, you would not get singularities. I looked at the paper, I didn't notice the mistake. There was a mistake in the paper. I just thought, well, that kind of method, I'm not quite sure I would be convinced by doing it that way. So I didn't trust the paper, which was lucky.
Right.
Because there was a mistake in the paper, and I thought maybe that's the wrong answer. And I started imagining, I remember going walks through the woods and imagining that I was in the middle of a cluster of stars maybe collapsing. And
so again, imagining the thought experiment, the visualizing.
Was very much visual thinking, yes.
So the Kalatnikov paper, so 1939 is the Oppenheimer paper. It's many years. It's kind of obscure. It's waffling in obscurity.
Well, it was a very important paper at the time, and I certainly knew it well. But I didn't think it was realistic. People generally didn't think so. Because, as I say, it's exactly symmetrical. It's got nothing else to do but fall inwards to the center. So it's not realistic.
So John Wheeler, who's very influential, dismisses this work. He's very critical of Oppenheimer's work, isn't he? And then Kerr comes along and when would Kerr's paper?
Kerr was a little before my paper.
So he has slightly...
I refer to it, yes.
Slightly more complicated. It's now a spinning black hole.
That's
one
right.
step more complicated.
Yes. That's so you can imagine a spinning version of the original solution due to Schwarzschild, which was the spherically symmetrical case, and if it spins...
And how is that received?
Sorry?
How is that paper received?
I don't think people paid too much attention. I mean, I think I quoted it in my paper. I was aware of it, and the fact that it had this. Well, you see, there's a thing called a trapped surface. I don't know if you could see it in there.
Is that B3?
The words may not be.
They're not on there. I think that's your B3.
You see, the idea.
I don't see it. Yes.
Well, I could tell you the story of how that came about. You see. I was being visited. I was in England. I had a job at Birkbeck College in London, and Ivor Robinson, who was a good friend of mine, and he was a very good physicist, but he never wrote anything down. He did it all by talking, and he would get a colleague to write everything down.
Gosh, I wish I could do that.
Yeah. Well, he never wrote. I think he wrote one paper, but I'm not sure. It was always somebody else did the writing. And he was very good at talking things. So he'd come to visit me, and we were walking towards Birkbeck College, my college, and I remember he was talking and talking and talking, and then we crossed the street, and then we got to the other side. And then when he went away, I remember having this feeling of elation. I thought, what am I feeling so happy about? And I thought, I must have had some idea, which I can't remember. So I went through all the things.
So then you were sad.
I thought about what did I have for breakfast? No, it wasn't that. Was it my walk through the woods, which I usually did to catch my bus? No, it wasn't that. And blah, 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 blah. And then I thought, it was going crossing the street. Ivor was not able to speak because we were looking out for the traffic. Those few minutes when we crossed the street, I'd had this idea. And the idea, I don't know if you can see it very well in the picture, it's a thing called a trapped surface. The thing was, how do you characterize the fact that the collapse had gone too far? It had gone past the point of no return, but in a way which didn't depend on symmetry. You see, the Oppenheimer-Snyder paper was assuming exact symmetry, so you couldn't trust it. I mean, everything's focused to the center. That's no good. You have to think of what's, in a general case, could characterize a point of no return. And this was this trapped surface, and The thing is, if you imagine it's an ordinary two-dimensional surface, you imagine a flash of light on that surface. It's a sort of instantaneous surface, flash of light. And if the light goes inwards both ways, that's the characterization.
Yes, your light cones
it's
pointing
actually
inward.
in that picture.
Yes.
You can figure out how the thing works. But that was the criterion. And if you have a trapped surface, it doesn't depend on symmetry or anything like that.
Right.
But if you get a trapped surface, then you're in trouble. You have to get this singularity, which... but it didn't necessarily say it was a black hole.
Yes.
I remember I gave a talk at King's College London on this subject. The movies had it all wrong because they had Stephen Hawking in the audience with sparks coming in her.
But it was
inspired by this lecture. He wasn't actually there. It's not quite so bad because I gave a repeat in Cambridge and Stephen was there. And I described my techniques to him and then he developed them himself. And the idea was how you talk about the general case. You see, you're not talking about exact solutions. You're not talking about specific solutions like the Kerr solution, which is important to know about.
Yes.
But it's only a very special case. So in the general case of collapse, and I think most people believe that it would just come swirling out again.
Right, that the singularity and the event horizon were artifacts of these very simplified models. And once you have this completely general result, it would show there's none of this
Once you have a
nonsense.
trapped surface, which is a general thing, you can perturb it and it's still trapped, you see.
It's still trapped, exactly. So it doesn't matter how complicated it is on the inside, it's a proof that now you've formed this one-way phenomena. It's never coming out again.
Yes.
Yes.
No, it was...
Did you understand right away, so now back to that original question, did you understand right away, it's a remarkable paper in its elegance, but also its brevity. Did you sense right away the significance, the impact it would have?
I'm not sure. It did actually have quite an impact, I remember, because people were... Well, a lot of people didn't believe... I remember some people didn't believe in black holes at all.
All the way into the 90s.
I remember Phil Morrison in particular, was a very distinguished scientist, and he didn't believe a word of it. And I remember Bob Dickey, who was a very good scientist, and he came and slapped me on the back, and he said, "You've done it! You've shown general relativity is wrong." He was trying to promote his own model, you see. But what he didn't realize is his own theory actually suffered from exactly the same problem.
Yes, I remember Phil Morrison. He was at MIT, and he was a holdout against black holes, even when the observations were very, very suggestive.
He didn't believe it at all.
Yes.
No, there were lots of people who didn't believe. Well, they didn't believe in general relativity. It was like Bob Dickey, you see. General relativity didn't have the sort of firm status as it does now. So there was a reasonable... You could reasonably object to the theory, but I was certainly pretty convinced it was right, but right to the extent that it, in a sense, has its own downfall and it predicts these singularities that you can't avoid. But the argument was completely general. You had to have this thing called a trapped surface. That was the characterization of having a point, too far. Once you have a trapped surface, then you're done for.
Now, you're imagining gravitational collapse in a curved space-time, but without resistance. You're not thinking...
But the Kerr solution also has a trapped surface.
Yes, exactly.
It's just a special case.
So did you think, okay, this is still math, or did you think, oh no, those quasi-stellar objects that people are talking about, that they don't know what they are, that are very bright, that are this mystery, did you think, oh no, these are real in nature? Do you think they're out there in the universe?
Yes, I think I thought it was real, yes. No, it was not, to my mind, sort of
just a game,
mathematical fiction or something, no. Well, I think I was a strong believer in general relativity, and if you believe general relativity, you have to believe this.
Now, you believed in general relativity, but even you said, you had a phrase in that paper that's lovely. You said, well, I really don't think that the singularity exists, but you give some reasons why. Maybe quantum mechanics, maybe your ideas about space-time aren't right. The trapped surface exists, but the singularity on the inside, so we should talk about that. Maybe that doesn't exist inside the black hole. And you said it's sort of, how did you describe it? An attitude of mind. Whether, which of these reasons you suspect to be right. But tell people why the singularity is different from the trapped surface.
Oh, it's a different place. You see, the trapped surface is way out there. It
could be huge.
Huge. Where the singularity, well, you see, we don't know really anything about the singularities. I should say that the paper by Lifshitz and Kalatnikov actually had a mistake in it. Yes. The mistake, I think, was, I didn't see the mistake. I never looked at the paper carefully enough. I think Charlie Misner, who was a colleague of mine at Princeton at the time, he was one of the people, I think. I'm not sure. Belinsky was probably the one who saw the mistake, because there was a follow-up paper.
Belinsky,
Klatnikov. That's right. And it came to the opposite conclusion, that singularities were generic, and they had some general description of the absolutely vilely complicated these things were.
Right.
And Charlie Misner also came to a similar conclusion. So the singularity is extremely complicated.
Yes.
And nothing like the sort of smooth outside that you get with black
It was a
holes.
chaotic approach to the singularity, as I mentioned.
And the view would be, the view would be that to understand what goes on there, you have to have quantum mechanics or quantum gravity or something. But the trouble is, it's a sort of dead end. You can work on quantum gravity, and maybe you could have a theory which you think explains the singularity, but it doesn't do you any good, because they're right inside the black hole. They don't affect the external physics at all.
And we'll know nothing about it. So once this trapped surface, so you have this collapsing star. Once this trapped surface forms in these complicated systems, the star can no more sit there than it can race outward at the speed of light. Right? So it has to continue to fall.
And it also needn't be a star. So I was imagining also in clusters you might have it form. You might have a whole lot of stars, and they would form a trapped surface around them. And then they would form a huge black hole.
Right, and then in the interior, sometimes people imagine, oh, there's this dense material from whatever it was that formed the black hole, but it's forced inward. It's forced inward. It's forced to, in pure general relativity, it makes the singularity this regions of infinite curvature. But you think that something else happens there. You get close to that moment when there's an infinite curvature and a singularity, and then our laws are wrong, our understanding falls apart.
Well, it's probably some form of quantum gravity, but the trouble is it doesn't help you.
It doesn't help you,
I mean, even if you had a theory of explaining all that, well, it would be nice to have a theory. I don't believe any theory of quantum gravity I've ever seen, but that's not the point. Even if you had one, it wouldn't give you anything observable that would be useful. I mean,
because it's behind.
Yes. Now there's a little bit of a catch here, a big catch, I should say. Namely, there is a place where you have a singularity which does affect us all, and that is in the Big Bang.
Indeed.
So people would argue that that's sort of what you might expect in the Big Bang. And I had a lot of trouble with this. Years and years worrying about this because they're so different.
The Big Bang singularity.
Versus the
center.
Different.
One is in time. It's a singularity in your future. And,
well, one is very irregular and complicated, and the other is very regular. And oh gosh, well, I can tell all sorts of stories. Shall I tell you one of my stories?
Please, yes. That's what we're here for.
Yes, this was important in understanding these things. I was giving a talk in Caltech. I have to tell the story slightly backwards, because I learned later that Feynman, famous physicist, Richard Feynman, wonderful man.
Also thought in mathematical pictures.
Oh, yeah. No, he was a great physicist. And he had apparently seen a poster of this talk. And he told a colleague of his at Caltech, he'd said, I'm going to go and heckle this guy. Okay, so I start giving this talk, and it was about the expanding universe and what's special about. But I'll come back to that in a minute. And somebody sitting behind Feynman, I presume it was some Nobel Prize winner or something, Caltech's full of them, and he started to heckle me. Feynman turned around, pointed at the man, and said, "You shut up, listening to what the man's saying."
So you convinced him?
Yes. No, Feynman picked it up very quickly. No, I have a lot of respect for Feynman.
So let's talk about quantum gravity. It's been many decades since people have understood that, in some sense, general relativity was signaling that it needed quantum gravity. Right? It's saying these energy scales, the exaggeration of the space-time. It's calling for both the quantum and the gravity. Are you disappointed we don't have a theory of quantum gravity yet?
Not really, because it's the wrong answer.
What's the question?
Yes, what's the question? Yes, now you see, it's the whole, I've struggled with this, well, partly starting from this talk where Feynman was present. And what I was trying to understand, you see, the second law of thermodynamics is very important in this story. What does it tell you? It says entropy increases. Well, what does that mean, really? It tells you that the randomness increases. And in this talk, which Feynman was present at, I gave little pictures I had. I like to do it in pictures. And one was a gas in a box or something. And you imagine it tucked up in one corner. You open the box, it spreads out through the box. Entropy increases, uniformity increases. What about gravity? If you have stars, it goes the other way. As the entropy increases, they get clumpier. So it goes the opposite way.
Yes.
So that you start the universe up very uniform. This is consistent with being high entropy in electromagnetism and all these other things, but low entropy in gravity, because gravity goes the other way. That is to say, uniformity means low entropy. So what's special about the Big Bang is that the gravitational degrees of freedom were not activated for some reason.
So in some sense, the universe started in a lower entropy than we would anticipate?
But low entropy in gravity, but not in everything else. Very strange. So what's so special about gravity? I struggled with this for years and years and years and years, until I came to an answer which, I'm not sure, people don't like this answer sometimes. I like it. What is the answer? How do I put this now? You see, the Big Bang is very, very special in that the gravitational degrees of freedom were somehow not activated. Now, it was really my student Paul Todd who was pointing something out to me about this. How do you describe you see, you want to say the early stage where the gravitational degrees of freedom, I want to be a bit technical here. I'll say that the gravitational degrees of freedom are described by what's called the Weyl curvature. The curvature of space-time splits into two pieces, basically. And the part which describes matter, that's the Ricci curvature, and that's all Einstein's equations. And the part which describes gravity is the Weyl curvature.
And we often ignore that.
Yes, it's the part that the matter doesn't know about. When you write it in normal tensor form, it's a great mess. But I like doing things in two spinners. Let's not talk about that. And it looks very beautiful if you do it that way. And I like the things which look beautiful. And you could see this Weyl tensor is a very beautiful structure. And it describes gravity. But for some reason, it's zero at the beginning. So this is just sort of, you might say, an observational fact. We don't directly observe it. But to say that the gravitational degrees of freedom were not activated at the beginning is to say that the Weyl curvature is somehow not there at the beginning. It's zero. You have this enormous curvature at the beginning, but it's all in the other part. it's not in the gravitational degrees of freedom.
So you think this is a hint to the quantum gravity story?
Well, you see, it's not. I thought it for decades, yes. For decades, that's what I thought. I thought, gosh, quantum gravity must be a very peculiar theory because it's telling you that gravity behaves very differently from anything else. No, that's not my picture.
So after all of these years of people trying to take these degrees of freedom in gravity and literally quantize them to try to make a microscopic description and failing. The math is very resistant, it's very nonlinear, there are infinities, it's unwieldy, to string theory, which are attempts Don't touch it. Do you go to string theory lectures and heckle them?
No, I don't go to the lectures.
That's a missed opportunity.
No, I should.
What is it that's untouchable about string theory? Just briefly.
It's got the wrong number of dimensions. No, when I first heard the idea, it was a beautiful idea. I thought, yeah, that's a really nice idea. And it was a nice theory. But then they said, oh, no, it doesn't work in 3 space and 1 time dimension. You've got originally 26 dimensions. No, thank you very much. You take it away. I want a theory for 3 space dimensions and 1 time dimension. That's what we know. That's what we study. That's the universe we know about. Don't tuck it up all in little tiny things. It doesn't work. So, that's. I'm afraid I was never tempted by that. I was tempted originally, but when it got up to 20, well, coming down to 10 wasn't much of an advantage. No, that didn't help at all.
But you know, in the very early days of Einstein working, when he starts to discuss space and time as dimensions, it was natural to ask, well, why 3?
Yes, no, it's a good question.
Yeah.
Absolutely a good question.
And did you wonder about that?
Oh, yeah. No, well, you see, I like 2 dimensions. 2
so
complex
why 3?
dimensions. You see, I don't want to go into that story. No, when you do it with spinners, it's beautiful.
Yes.
You have 2 dimensions, two complex dimensions. That's a different story. Don't get me into that at all.
So you're open to the idea that there's higher dimensional universe, that a higher dimensional universe is conceivable.
Conceive it, but it's not the one we live in. No, I don't know. You see, there's so much about how the physics works so beautifully when you've got 3 space and 1 time dimension. And the mathematics works beautifully if you do it this other way. And this is another story which I shouldn't get dragged into, I think. Or I'll go off into one of my...
one of your tangents.
One of my tangents, yes.
Well, let me ask you this. Do you imagine that our Big Bang was the only Big Bang?
No. But in a different way from what most people think. Yes, you see, I should continue that story. It's a story I've been plugging since about 2005, I guess. I'm not quite sure when I first put it forward. Nobody believes me, except my close colleagues. I have a lot of good friends, most of them Polish. And yes, there are some people who take me seriously. No, I'll tell you a picture, and it just to deal with this problem. You see, how do I put this? There's a kind of geometry which describes space-time. It's called Riemannian geometry, or pseudo-Riemannian geometry, technically, where you have a notion of distance. Or really time is the better way to describe it. But more important is the light cone structure. That is, if you have a flash of light, it goes out in the sort of sphere which expands, and this describes a structure in space-time which is called the null cone or the light cone. And these light cones are more important than the geometry. They're not, you see, the metric tensor has 10 components, 10 numbers described.
So the field that's describing the curvature of space-time,
yes,
essentially.
it describes, at one point, you've got this metric which has 10 components. 9 of them describe what I call the conformal structure. Now, the conformal structure It's a very beautiful kind of geometry where you don't have size, you have angles. And people may be familiar with these beautiful pictures by M.C. Escher, where you have what you call circle limits. You have a whole universe, angels and devils in this, within the circle. And then you see infinity is the boundary.
Asymptotes to this infinite
So you can talk about infinity in this conformal way. So that was a great, I used to enjoy talking about infinity.
And your Penrose diagrams, your famous and widely used diagrams, maps infinity into these finite bounded regions.
Right.
Yeah.
So it's a nice, I was familiar with the idea of squashing infinity down.
It's like a map that distorts the reality, but you can see it all in one eyeful.
Yes. Now the opposite, basically partly due to my student Paul Todd, I may say, and he suggested to understand the specialness of the Big Bang, you stretch it out. Squash down infinity, stretch out the Big Bang.
Okay.
If you can stretch out the Big Bang so it's nice and smooth, that describes the way in which it's special. And the Weyl curvature is very strongly restricted. Zero, or depends on how you put it. So the Weyl curvature is pretty well not there. But you can stretch it out and make it a nice smooth surface. You can squash infinity down and make it a nice smooth surface. My crazy idea is that the Big Bang is the continuation of the remote future of somebody else. A previous eon, as I call it, cosmic eon, and it has its Big Bang. The universe expands. Now I should explain why it's legitimate to think of this very hot, squashed up beginning is very, very much like this very cold, stretched out remote future. And the argument really is that what is it that determines the scale? It's mass. It's the two most famous formulae of 20th century physics put together.
I know one of them. E equals mc squared?
E equals mc squared. That's Einstein, of course. E equals h nu, hf, if you like, even before Einstein. That's Max Planck. Max Planck. Einstein tells you energy and mass are equivalent. Planck tells you energy and frequency equivalent. Put them together, mass and frequency are equivalent.
So you can
mass
exchange
is what gives you the scale, that's frequency. So if you don't have any mass, you don't have any frequency. Now where don't you have any mass or don't you have any frequency? In the very remote future.
When everything's dilute.
It's more or less photons.
And
there's a bit more
left.
of a story there, but it's more or less photons. Don't have any mass. Nothing mass to give the scale. What about the Big Bang? Well, the energies get so enormously huge that the mass becomes irrelevant. If you have to know a little bit about how you describe mass energy in relativistic physics. But the thing is that the mass scale, again, gets lost. It gets lost because everything's moving on so fast that they more or less have no mass anyway. Two ends, Big Bang, remote future, you lose mass.
So are you imagining a cyclic series of Big Bangs followed by this asymptotic future, which is conformally somehow mapped back to the singularity?
Yes.
Would you see an increase in entropy each time this happened?
Well, the entropy, people are complaining about
signatures?
the entropy. You see, I'll tell you what happens to the entropy, if you like. Where does it go? Even now, the entropy in the universe is absolutely dominated by black holes. The black hole entropy completely swamps, even now. It's going to get black holes swallow things, they get bigger and bigger, galaxies get swallowed up by black holes and things like that. The entropy goes up. It goes into the black holes. That's where the entropy is. What happens to the black holes? They sit around and they sit around and they sit around until the Hawking temperature of a black hole, which is extremely cold, I may say, and the very big ones you're going to get, is ridiculously cold. They wait and they wait and they wait until the universe gets even colder. You have to wait for something like 10 to the 100 years. Think of one with 100 zeros, that number of years. A bit more than that, actually. You have to wait for a bit more than 10 to the 100 years by the time that the universe cools down until it's lower in temperature than the coldest black holes, and then they start to radiate away. Doesn't matter much, actually.
It doesn't matter much?
in this picture, even though they're huge, they're so small that they don't even make much of an effect. They're what we call Hawking points.
Yeah.
I wrote a paper with my two Polish colleagues and another one.
So in some sense, our future could be that we fall into this supermassive black hole, Sag star, one day, and everything that can fall into black holes does.
It gets crunched up into the singularity.
And then the black holes lumber around for an eternity nearly. And then they slowly begin to evaporate, very slowly.
Yes.
But in the end, they explode away.
They evaporate in basically photons. But it doesn't make much difference because the rest of the universe is stretched out so much that these are actually very localized. Well, you see, I can tell you what happens to them. In the next eon, you see, at the end of the previous eon, you glue that on to the beginning of the next one. That's our Big Bang. And all that energy comes through. You can prove a little theorem which tells you that the energy is not lost. It comes through into the next eon, and it makes little spots. And these little spots are what we call Hawking points. And we wrote a paper, gosh, it's getting on for 10 years ago by now. Nobody paid much attention to this paper. Very respectable journal, the Monthly Notices of the Royal Astronomical Society.
Very respected.
Very respectable journal. And it's there, sitting there. You can look at the paper. And we say these Hawking spots are there. And we see them. And we identify, I forget how many, probably about 5 of them. The list goes on, but I don't believe most of them in the list. I believe the 5 strongest ones. There's good reason for believing those 5 ones. Because they show up in different maps, in exactly the same places.
So you're saying that not only would there have been a previous Big Bang and maybe an infinite series of previous Big Bangs, but that we could see evidence of those Big Bangs because of black holes.
We claim that we see them, yes.
And that you see them.
No, this is a paper. Nobody's refuted it.
Did you say this was a crazy idea? Yeah.
Yes, it's crazy. It's just about crazy enough to be true.
So I know people, I promised at this juncture to allow for a Q&A, and I know Stephen's going to help me, but just before I hand it over to other people's questions, I did want to say it's since 1965, it's 60 years. There have been all of these observations. You've seen a picture of the shadow of a black hole. Has it been remarkable to see the observational side, which is not your area, just to watch the field unfold?
This morning, I was watching one of these from China. There was a wonderful program. They were showing pictures of black holes and how they could work out which way they're spinning and whether it's actually a Kerr solution. I found it very striking how much information they can tell about these actual black holes. And it seems to be a well-supported area of observation.
It's fascinating. It's been a century of black holes.
Yeah.
It really has, this new century. Before we open it up to questions, can you just join me in thanking Sir Roger for his thoughts?
Thank you, Janna and Sir Roger. That was inspiring and wonderful. So we do have time for some questions. We do have people here to run the microphones. So we've got 2 people here. Just turn it on. It's on. Yeah, thanks.
Can you hear me?
Yeah, can you just push up? Is the button up?
It's up.
You see a green light? You see a green light like this?
There's a green light.
Oh, there we go.
That's you.
Yeah.
Hello. I was interested by your response to what's your thoughts about what's your main gripe with string theory, and your response of it's got the wrong number of dimensions.
String theory, yes.
I can relate to the idea.
I'm sorry, I'm probably too biased. I should shut up. But no, as I say, I was quite struck by the idea when I first heard about it. I thought it was a very nice idea. I mean, you can make these Feynman diagrams into things which look finite and so on. And I thought that looked really nice. But when you see, when it became 26 dimensions rather than 4, that was to me say, okay, I'm not doing it. But then it became 10 dimensions at the same as 26, or at the same time. And then I think 11. I mean, I just can't make head or tail of it. Mm-hmm. And also, you see, the idea is you get rid of all the extra dimensions by tucking them into tiny little spaces. The trouble is, I shouldn't go into the technicalities. Mm-hmm. I mean, I just don't think it works. Mm-hmm. I really don't see there's any benefit in looking at, I mean, there could be other universes with higher number of dimensions or something, but that's not our universe, so I'm not really concerned with it. Mm-hmm. To say that our universe has all these dimensions tucked up in little balls or something doesn't really make sense to me. Partly because part of the argument is you need too much energy to excite the energy in these little balls. The trouble is that that's not the right argument, because the balls are spread out over the whole universe, and you have easily that amount of energy in the whole universe.
It's quite hard to keep them small.
It's just, I never could trust those theories at all.
I won't show you my paper from Monday.
Oh, have you got one of these papers?
I just put one out on Monday. It's only 6 dimensions there.
Oh, I see. Well, even that's too many.
Could you pass it to the middle there, please?
So you mentioned that for gravity, low entropy is uniformity is low entropy, and that's different to other things. Why is uniformity low entropy for gravity, but not for other forces like electromagnetism?
Well, you see, the entropy goes into the black holes and whatever they radiate into. If they, I mean, they should radiate away. There's a slight question about whether you necessarily believe that. I do believe it. I think Stephen Hawking is right there, that they would radiate away eventually. It takes an awful long time for it to happen, but the entropy is squashed up into those tiny little... See, in the crossover from one surface to the other, these little points are so small that they're smaller, much, much smaller than what's called the Planck scale. So that's much smaller than the scale where you would conceive even quantum gravity to be important. So we have no idea what goes on. The only thing that, according to the theory as we work it out, you would actually, the mass of these points would not disappear. You can prove a theorem which says that the mass continues through onto the other side. And my colleague Christoph Meissner did a calculation to see whether this mass, I'm trying to think now, was plausible for these points. Yes, this, what we call Hawking spots, you see. Well, we're calling them Hawking points because they are probably the Hawking radiation all squashed up into a little point. And when they come through on the other side, you get a little heated region in the microwave background. And these heated regions are seen, and we call them Hawking spots. That's in the paper. I don't think, as I say, anybody's paid any attention to the paper, but it's in a respectable journal. Mm-hmm. And these spots are there. Mm-hmm. The spots are seen. I would say probably about 5 of them I trust, because there's sort of the smaller ones are probably, there could be fluctuations or something. But the biggest ones are probably really there, particularly because the analysis was done on two different satellites. You see, there's the Planck satellite and the WMAP satellite. These are two different satellites which are sent up to look at the background radiation. And you see these spots at the same places in both satellites. These are the 5 strongest points. So I believe those 5 strongest points are real Hawking points. And if you work out the intensity of these spots in the sky and compare that with the biggest clusters of galaxies, they're about comparable. According to Christoph, my colleague, he worked it out, and he was very proud of the calculation, I think worthy of being proud, that they do come out pretty well consistently, that the spots that we see in the sky, they're there, could well be what you call the remnants of galactic clusters, big galactic clusters. They will not, see, the galactic clusters remain bound. As the universe expands, these clusters remain bound together so that they don't expand with the universe. They sit there and produce black holes, and the black holes collide with each other and they swallow each other up until you end up with one big black hole that sits around and sits around and sits around until the universe gets colder than it is. It takes a long time, 10 to the 100 years or so or more, and then they radiate away and form these. It's a picture which seems to be consistent. I don't know whether anybody else believes this, but, as I say,
I'm going to ask you more at dinner.
Published in a respectable journal.
I'm going to interrogate you at dinner. How infinity becomes zero. That'll be a conversation.
Oh, it's not. It never comes infinity. You see. I see. You mean infinity?
Yes. Yes.
Yes. But that's because you lose mass. Yes.
Yes. Yes.
So it's a conformal structure.
So unlike the expansion of the universe, we are up against the time deadline here. So finally, I would like to ask the Chancellor of the University, an expert, another expert in this area, if he would like to say a few words to sum up. Lord Heath.
I'll borrow your mic. Well, thank you. That has been absolutely fascinating, even to a non-physicist. Of course, in my old profession of politics, we also have black holes. As you know, in fact, every incoming government discovers a black hole. And astonishingly, they can measure the dimensions exactly. Even now, the Chancellor of the Exchequer is trying to fill in a black hole.
Yes,
but now I know enough to assure them that in the end, these radiate away. Rachel Reeves will be so delighted to hear. But of course it has been fascinating, and I speak as a non-physicist, but what a pleasure to be able to listen to Janna, and always such a pleasure to listen to Sir Roger, and to have them able to reflect with so many students and faculty is absolutely what it should be like in Oxford, an absolutely fascinating evening in a very important department of the university, I stress, and I don't say that, well, I probably do say that in all of them, but I know this is a particularly important one, and I've been very interested to learn what I've learned so far about the work of the physics faculty, and particularly in the quantum field, for instance, and to see what I've seen, which I think is very important to the university, critical to the success of the United Kingdom, and indeed very important to the future of humanity, knowing where it is in the universe. And I particularly want to thank Lord and Lady Hintze for their tremendous support for astrophysics in Oxford. I have actually known them for a very long time, but I don't know how long, 30 years or something like that. And I had no idea until I came back to Oxford recently that they do this for the university. And I know them through politics, through business, socially. Actually, one of the best birthday parties I've ever been to in my life was Michael Hintz's birthday party. So if you get to know him well, you'll really have a good time. But when I heard about their support for astrophysics in Oxford, I was not surprised. because generosity and intellectual curiosity are really their hallmarks. And I hope they really took from the film at the beginning the message that there are so many brilliant young people who benefit from that generosity. And to celebrate that with this 30th lecture tonight is a very fitting way to do it. Oxford tremendously values your support and enthusiasm and your involvement. So thank you for that 30 years and for everything we know you're going to do in the future as well. A big round of applause for Michael and Dorothy. Immensely valued, and thank you for having me along as well, and I think it must be time for a drink.
Yes.